Hello everyone, my name is Brandon Bills, and today I'd like to walk you through my poster on moving beyond data-dependent MS2, and we'll talk more about how you can improve annotation confidence in untargeted metabolomics using higher resolution as well as parallel experiments in the ion trap. We'll start off with the abstract. First off, the purpose. The purpose of this work was to get better elemental formula confidence by using a higher Orbitrap resolution to get a more resolved isotopic fine pattern. We also looked to improve annotation confidence through supplementary MSN experiments, as well as collecting breakdown curve data in experiments that can be run in parallel if run within an ion trap. As far as the methods go, we were looking at NIST 1950 SRM plasma extract on the thermoscientific Orbitrap IQX driver mass spectrometer. We used AcquireX to iteratively analyze the sample, incorporating data-dependent MS2 along with data-dependent MS3 in the ion trap, as well as data-dependent MS2 with breakdown curve data for those MS2 collected in the ion trap. Then we evaluated the impact of that data on the confidence of compound annotations. What we found, higher resolution gave an improvement of the resolution of the isotopic fine pattern, which can help differentiate isobars, which was particularly important for compounds above M/Z 400 because you've got a lot more isobaric formulas within 1 ppm mass accuracy. We also showed that we can get improved annotation confidence using that additional ion trap data. And we also showed that MS3 data could provide extra criteria for comparing against MC Cloud or using fish scoring, which helps you differentiate compounds with very similar MS2 results, but that had differentiation at the MS3 level. We also looked at how breakdown curve data can give you some additional data compared to what a stepped collision energy can give you. So let's start talking about resolution and elemental formula prediction. This first table here talks about the number of theoretical isobars within mass tolerance, as well as the number of isotopic fine peaks you can see at different resolutions. Now, you can see along the left-hand side, we have a number of compounds that we found in NIST 1950 at a range of M/Z values from around 150 M/Z all the way up to around 750 M/Z. We can see that when we're at lower M/Zs, around 150 with cysteamine and phenylalanine, the number of theoretical isobars within your mass tolerances is fairly low. So at lower M/Zs, it's pretty easy to get an accurate elemental formula. But as we go up to palmitic acid and biotin, we can see that we start to get more theoretical isobars, especially when we start adding in heteroatoms, especially like nitrogen, oxygen, sulfur. We see that palmitic acid might not have a lot of theoretical isobars, but biotin has a significant number, having even 3 within 1 ppm. We continue up 100 more into the range of maltose and 3-AMP. Now we're looking at around 6 to 9 isobars, and it just goes up from there. So we can see that as we go to higher M/Z values and add more heteroatoms into the structure, we have a lot more isobars we have to try to resolve. And typically we try to resolve that using the isotopic fine peaks. These are the peaks for those heteroatoms that can be distinguished at a high enough resolution. Now, in the middle of the chart, we see the number of the isotopic fine peaks we get in the A2 isotopic fine peaks. That's 2 neutrons throughout the molecule. we can see that at 60K or 120K, most of the time you're only going to see one peak resolved in that cluster. It isn't until you get to 240K resolution that you are really seeing more than one isotopic fine peak. And really 500K is where you start to get 3 or more. And these are all very useful when you're trying to figure out which isobar you actually have. Take, for example, this compound at 496 m/z. We can see if we look at the A2 cluster, we find at 60K and 240K resolution, we don't have any isotopic fine information. We just have everything averaging together. We get up to 500,000 resolution, we can see at least 3 peaks, plus we've got a bit of a shoulder on that middle peak that can give us quite a bit of information on the isotopic pattern. But once we get to 1 million resolution, we can clearly see 4 peaks resolved here. I'll point those out now. Now let's look at the actual potential isobars this could be. Here we see the various predicted isobars for this compound within 1 ppm mass accuracy. Now we've got 4 different isotopic fine peaks we could be looking at. We've got the carbon-13 with the nitrogen-15, one with an oxygen-18, we have 2 carbon-13s, or we could have a carbon-13 with a deuterium. Now we know from the previous figure that we've got at least 4 peaks to look at. So we know the bottom pattern can't be correct. We also know that there was a lot more of the oxygen-18 peak than the carbon-13 plus nitrogen-15 peak. So the left pattern isn't quite right. So if we look at that distribution again, these are the same arrows from the previous slide, we can see that the top right pattern is the most likely out of these isobaric elemental compositions. So this is just an example of how having that extra resolution really helps give you confidence about predicting unknown elemental formulas. Now, how does this look if you look at all of the compounds in the sample? To get at that, we pulled out all of the compounds that were discovered that were over m/z 400, because that's where you're really going to see these changes, and checked at resolution 60K and resolution 1 million, and checked to see how many of those compounds had the predicted elemental composition change once you had 1 million resolution and had that isotopic fine pattern resolved. So going from no isotopic fine peaks resolved to everything at 1 million, we found around 85% of the elemental compositions that were predicted within Compound Discoverer changed as a result of having that isotopic fine pattern. So that gives you an idea of how important it is to have as much information on these peaks as possible to be confidently annotating your unknown compounds, especially when you're over m/z 400. Shifting gears, let's talk about what ms⁻³ data, which can be collected in parallel in the ion trap, can do for confident annotations. As an example, I pulled down these spectra for acetaminophen and 2-acetaminophenol from MZ-Cloud. And we can see that at collision energy 40, acetaminophen and its isomer, 2-acetaminophenol, are very similar to each other. There is a slight difference in the ratio between the 92 and the 93 fragment, but these are still very close to each other in terms of their spectra. What we see is when we subject the 110 fragment for these two positional isomers to an additional round of fragmentation, going to ms to the third, there is now a significant difference. We can see this 92 fragment is much more intense than it was at the ms2 level, and that gives quite a bit of confidence that if you see a lot of this 92, you have the 2-acetaminophenol. So that was a good example of what you can do when you have example data in MZ-Cloud. What if you don't have MZ-Cloud data to look at? What if this is a true unknown that you have to try to figure out what it is through potential structures that you feed Compound Discoverer? Well, Compound Discoverer can do fish scoring or fragment ion search at the MS third level as well. So by providing it a structure and MS3, it can not only find which potential structures have the most matching fragments to the predicted fragmentation pattern at the MS2 level, but it can also take that a step further and look at the MS3 level and tell you how much of the MS3 fragments are also predicted. And that can rank your structures and give you some more confidence in your unknown annotation, even when you don't have matching library data to look at. Now, in our final section, we're going to be talking about breakdown curve data. This is the idea that we can collect individual collision energy data and compare that against stepped and find some information that isn't captured when you're just doing an average amount of collision energy. So we have two similar isomers, paraxanthine and theophylline, with a predicted stepped collision energy of 40, 60, 80. We can see that there's some differences between paraxanthine and theophylline here, but it's kind of difficult to tell them apart just on this data. Now, if we use the ion trap to collect multiple collision energies, we can get a bit more information about how the breakdown happens as you add more energy. For example, we start at the bottom at 20 collision energy. Here we can see they're very similar. As we go up to collision energy 40, we see a much higher increase in the 124 fragment for theophylline than paraxanthine. Take that up to collision energy 60, and we can see that theophylline now has this 69 peak and 96 peak coming in, which is not really showing up in the paraxanthine. Check this at 80 collision energy. Now it's very different between the two spectra. Theophylline has a lot more of the 69 and 96, where paraxanthine is still largely this 124 fragment. If we take that one step further, we can see that paraxanthine is still dominated by this 124 peak, but it also has this 55 peak, which is just not showing up in theophylline. Where theophylline is really mostly gotten rid of the 124 fragment for these lower mass pieces. It's safe to say that if you were looking at just stepped collision energy, you might be missing out on some critical information. By having a few additional pieces of information that can be collected in the ion trap, we now have a lot more confidence in our annotation for these two isomers. So, in conclusion, higher resolution gives you more of your isotopic find pattern, which helps in your elemental prediction. MS3 data provides additional data for library comparisons, as well as unknown characterization through fish scoring. And breakdown curve data can give you some additional information that isn't captured strictly through stepped collision energy. And I would like to thank you all for your attention. I'm happy to answer any questions anytime. You can reach out to me at brandon.bills@thermofisher.com. And this information is for research purposes only, not for diagnostic procedures. Thank you.